In a previous video, we introduced the material ratio curve. If we have a surface that's kind of bouncing around doing things like this, the material ratio curve tells us where is the material. As we slice our way down into this surface, we encounter more and more material, and we end up with a curve that might look something like this, describing how much material from 0 to 100% we encounter along the way. Now, a surface like this is kind of random, and it's interesting sometimes to determine the standard deviation of things that are random. If I look at where are the points in this surface, there are a few points out at the edges, but most of the points are in the middle, and we end up with what we've seen throughout our lives as the thing called the bell curve. So there's a bell curve of points along the height dimension of this surface. There are lots of points in the middle and a few points that are beyond that. Now, one of the measures of a bell curve is the standard deviation, the sigma value. And before we had calculators, we had to do a graphical trick to calculate a standard deviation of a bell curve. So that graphical trick is actually something we can use in surface analysis. Let's take the material ratio curve, and instead of plotting it from 0 to 100 with nice even increments, let's start in the middle at 50. And then we're going to compress things. So instead of 60, maybe the next one over is 70, and over on this side it's 30. But we're going to spread out as we get near the edges. So maybe over here will be 90, but all the way at the edge is 99. We're not gaining very fast at the edges. Over here might be 10, and all the way at this edge is 1. We're compressing the middle. We're squeezing the middle in on the graph. And when we do that, we can transfer the material ratio curve onto a probability scale. This is probability. This is a scale that's based on the bell curve. The bell curve has more points in the middle, and this axis has more points in the middle. So this bell curve of points turns into a material ratio curve, and when we push it onto this kind of paper, it turns into a straight line. The material probability graph is a graph that turns bell curves or normal distributions into straight lines. Now, this is a powerful tool because if my surface is made up of, say, a plateau with valleys in between, what I have is actually two bell curves. There was the original curve that made the valleys that might have been very tall or very extended with a big standard deviation. And then there's a new curve of the peaks that we put into it. And this new curve actually will have a line of its own. So in the probability realm, the probability graph would look like this. We would have the original blue curve meeting up with our new plateau curve. The material probability graph or material probability curve isn't really a curve in this case. It's two lines, and those two lines represent the two roughnesses inside the surface. So the material probability curve is going to be used for some other parameters in our parameter library. It all begins with the material ratio curve, but we're moving it to a special axis that's kind of compressed in the middle that straightens things out when they're random. A surface like a plateaued surface actually has two random pieces, so we get two lines in the material probability curve.